The impact of EOR polymers on scale inhibition for energy simulation. Hello everyone, my name is Célia Silva. I'm currently a PhD student at Heriot-Watt University working on the impact of EOR polymers on scale inhibition, supervised by Ken Sorby and Eric Mackay. Scale inhibitors are used to prevent scale formation in the reservoir, tubulars of production wells, and near wellbore. Polymer flooding is an enhanced oil recovery method widely used in the field. In almost all field applications of polymer EOR, partially hydrolyzed polyacrylamide (HPAM) has been used. During the residence time of the polymer in the reservoir, the polymers are likely to change molecular weight through mechanical degradation or oxidative degradation, or chemical composition via in situ hydrolysis of the acrylic acid groups on the polymer backbone. The main goals of this work are to understand the potential interactions between EOR chemicals and scale inhibitors, and also to understand the polymer adsorption kinetics. Having in mind the main goal of this project, that increased oil recovery maximizes the economic recovery of a field while reducing the carbon footprint, and this is one of the biggest concerns nowadays. To better understand the interaction between HPAM and DATPMP, static adsorption bottle tests were performed at 70 degrees Celsius for 30 days. All the solutions were pH adjusted to pH 6. The mass and volume ratio was set in 1:1, with 100 grams mass of sand to 100 grams polymer or 100 ml of scale inhibitor. The HPAM analysis was done by easy imine method, and the DATPMP analysis was done by ICP. The adsorption was calculated using this formula, which is the volume multiplied by the difference between initial and final concentration divided by the mass. In this study, we have done some sequential addition experiment with polymer HPAM and scale inhibitor DATPMP, as well as the study on the polymer kinetics and polymer degradation of HPAM. This study started with a sequential addition experiment of HPAM at equilibrium and then added DATPMP into the system. With this experiment, it was possible to observe that HPAM kinetic adsorption is very slow, taking around 360 hours, approximately 14 days, to reach the equilibrium. After the equilibrium, DATPMP was added in, showing that DATPMP adsorption shows a minor increase in over the 72 hours period. For the HPAM, the system is moving to the equilibrium, and it is able to further retard DATPMP adsorption. It is also clear that DATPMP is able to partially displace some adsorbed HPAM from the equilibrated HPAM rock system. Then a sequential addition experiment of DATPMP at equilibrium and then HPAM added into the system was also performed to evaluate the opposite scenario. After the equilibrium of DATPMP, known for 24 hours or less from the literature, HPAM was added into the system. DATPMP adsorption slightly decreases, however, within the experimental error, taking us to the conclusion that DATPMP adsorption is constant in the presence of HPAM. And HPAM adsorption increases over time in the presence of DATPMP at equilibrium. However, the total adsorption at each time step is lower when there is a pre-adsorbed layer of DATPMP present. These two sequential addition experiments were crucial to conclude that the adsorption level of HPAM is lower in the presence of pre-equilibrated DATPMP. However, the adsorption of HPAM in the presence of DATPMP showed an increase after approximately 500 hours. This could be an indicative that it takes more time to reach the equilibrium when DATPMP is pre-adsorbed. Viscosity analysis was performed for HPAM 1000 ppm and then compared with the 100 ppm HPAM adsorption over 30 days, 720 hours, where it was possible to observe that HPAM 100 ppm adsorption increases over time as well as the polymer degradation. And then a question was raised, are these results related or not? And to answer this question, the polymer adsorption and viscosity experiments were repeated under anaerobic conditions to study one of the potential polymer degradation mechanisms, the oxidative degradation. To answer this question, a comparison between the viscosity analysis for 1000 ppm HPAM and the 100 ppm HPAM adsorption over 30 days, 720 hours, under anaerobic conditions was done. This experiment was conducted into an anaerobic chamber since the early stages until the analysis, and it showed that HPAM 1000 ppm does not degrade over time. However, the adsorption of HPAM 100 ppm increases over time even under anaerobic conditions. And this answers the question raised before, that HPAM adsorption increases over time and is not related to polymer oxidative degradation following molecular weight, because the behavior is similar in the absence of oxygen. Oxidative degradation cannot take place under these conditions. I would like to thank you all for listening to this presentation about my PhD work. I would also like to thank all the sponsors for the support of FAST Group, also the Fast Track, and last but not the least to Energi Simulation Group for this great opportunity. Thank you so much.